Okay, the first question is write the ARM instruction that store the location 6000 to 6014, this value. Then subsequently copy the data into location 7000 to 7014. All right, so I already written the code for the first part. This is the code. Okay, I'm going to copy. Going to put it here. Okay, first you move this one to 6000. This is the memory location. Okay, the first loop, actually the first loop is to store the values into 6000 to 6014. Okay, because in the setting here, I'm not sure whether you can it only allow you to view memory content. Okay, it does not allow you to modify the memory content. I'm not sure whether you can modify it in the email later or not. Maybe some of it will. Okay, so the first loop is to store the value into the memory. So you can see execute, compare. So it will branch, it will loop 6 times. I will loop 5 times actually. Okay, then we will go, we'll go and see the memory, 6000. Okay, you can see that this value is stored. Okay, so you can see first you store 6000, then you add 4 into R2, the memory location, then add 1 for the counter, this is the counter, and you compare it with 6, all right? When it reaches 6, it will break the loop. Then the second part is to load the value from 6000 and store it in 7000. So this is the second part of the loop. Okay. This add 4 is to add the memory location. Okay. It will loop 6 times. Okay. It will loop 5 times actually. Okay. Then when you see the result, you can see 6000 and 7000 is stored 1, 2, 3, 4, 5. Okay. All right. So this is my solution. I already put it over here. Later, I'm going to upload it into the MMLS. Okay. Then the second one, the second solution is that you want to store it in a reverse order. Modify, so you want to store it in the reverse order. Okay. Reverse order. Okay, you want to store until 6. 1 until 6. So I think, so this one we have to reset. I think we saw 7. Then it will be. Okay. So let's run again. Execute. Okay. All right. So you can see until 6. Okay. All right. Right. So this one is the code. No need to save. Let's save it here. Here is. All right. Save it. Okay. So the second code is you want to do it in a reverse order. Reverse order. So the same thing. It's the same thing. First, you have to copy. This one should be 7. And this should be 7. Okay, the only difference will be you can see R3, you add R3 with 14, then you subtract it. Okay, the only thing you in R3 is you start wait. Start from, okay, and then you subtract R3 with 4. Okay. All right. So let's cut and paste the code and put it here. Okay. Then execute it, and then you see the result. You can see the memory content is reversed. Okay. So how do we do reverse? Instead of copy, how is it different from the previous one? For R3, instead of 7,000, you start with 7,014. All right. Then you minus. Okay. All right. So these are the two codes. I'm going to upload it into MMLS. Working code, which you see right in front of your eyes. Any question so far? So far, any question? Any question? Just for this week tutorial, this week submission, this Saturday, we put it on Monday lah, because Chinese New Year. Okay, just to do question 3 to 8 lah. Okay, mainly just copy only lah, most of you. Okay, just copy over lah, for it's something like a revision exercise. Okay. All right. Question number 3. Okay. So define the major function of a system bus. So the interconnection, you have memory interconnection, you have processor to memory or memory to processor. Okay. Either you write to the memory of processor write to the memory or memory write to processor. Okay. Then you have I/O write to the processor or processor write to I/O. Okay. And then you also have I/O write to memory. Okay, so this is using a direct memory access. Okay. So these are some of the architecture. All right. So basically, what I want to okay, this one you learn in the I/O, in the operating system. So you have communication pathway, connect 2 or more devices. All right. So they're using a shared transmission system. So it's a bus. So the signal transmitted by any device. Okay, what do you mean by bus? This is an example of a bus. So this 1 device, 2 and 3 device, they share the same medium, the same cable, the same copper track, pin, whatever you want to call it, the same channel. Okay, so therefore you call it a bus. Okay, so only one person can transmit at one time. Okay, a single person transmit, the rest can receive. They can choose to ignore it or they can choose to receive it. It's really up to them. Okay, so this is a bus. Okay, when you say a bus, how does it look like? So let's see, Google, go to PCI adapter. Okay. How do I make a big, how do I, since it doesn't allow me, this one. Okay, you can see here, these are the interconnection. From here to here is 32 pin. So it's 32 bit lah. So front and back, so it will be 64 bit lah. So you have, and then this one, from this pin is connected to all the copper thread on the circuit, which is the bus, all right? So this is example of a bus system in the motherboard. Okay, let's see in the motherboard, motherboard, PC motherboard. Yeah, it's two. So you can see here from here, isn't it? So it might be, depend on it, it might be 64 pin. So both sides, left and right, or front and back, when you plug in the memory chip. So when it connected to here, then in the motherboard, there is a bus. You can see all the pins here. These are all the bus. All right, whether it's data bus or memory bus or control bus, data bus, control bus, or address bus, you have to see the schematic of the motherboard. Okay, you can see here, there's also buses here. How do I see it? See here also got buses here. Okay, all right. Then they got layer out lah, layer lah. Then the motherboard you can see got how many layer? 2 layer or 4 layer. 2 layer means top and bottom lah. 4 layer means more complex lah. So it is engineering and design constraint, physical constraint. Okay, let me show you what are the physical constraints. Let me see how. Whether teaching. Okay, tutorial 5 explain. Okay, you see this circuit, you can see there's interconnection in it. So if you do it on one layer, you cannot do like this. The copper thread cannot cross each other. So this wire you have to put behind. The blue wire has to put behind. And the so you must, when you really design it on a physical board, you cannot just simply draw like this, all right? You have to make sure that this wire does not cross each other, or only cross once only. Okay, so that's the problem with the design. If you have 2 layers, the cable can only cross one. I mean, cross on the bottom. Okay, okay, some motherboard you got 4 layer motherboard PVC 4 layer motherboard. Okay, clear? Yeah. Okay. So do you have communication? Then you have a system bus that connect major. First, you have the data bus. So the data bus is for you to transmit data. Depending on your architecture, it can be 34, 64, or 128 bit. All right. If 32 bit, that means that you have 32 copper thread, 32 pin, or 32 lines coming out from the device. Okay. This is the width of the data bus. The wider, the better. Okay. So for memory chip, hard disk, all that, maybe it's 128 bit wide. Okay. Then you have the address bus. Okay. So you are accessing the memory let's say that in the memory on your RAM chip, you need to specify which address you are fetching the data from. All right, you cannot be fetching everything. So you have to specify the memory. So the memory is separate from the data. So you have to use the address bus. Okay, suppose you have a RAM chip. Each RAM chip is, let's say, a 4 GB RAM chip. So got address one there. So which memory location in the RAM chip you want to access? All right. So you have to specify it in the address bus. Okay. Okay. Then they also use I/O port address. So this I/O port address is to talk to I/O lah. In PC there is this I/O port address lah. Let's say you want to talk to the clock. Your each PC got a clock in it. Got some other device, all right? Clock lah, example is a real-time clock lah. So there's a port number for that. So there's a I/O port number for that. Okay? So let me show it to you. PC port number. Okay, not this one. Not this one. PC real-time clock. PC I/O port. So you can see here, these are the port number. Okay, can you see here, I/O ports? Can you see? Use what lah? No lah, you handwriting lah. Handwriting lah, okay? Handwritten lah, okay? Handwritten lah, okay? If you use word, then you all copy, direct, and submit. All right? No lah, use okay. All right. So okay. All right, where are we? So these are the ports number lah. Okay, you can see by yourself. Okay, then you have a control bus is to control user address. Whether you are using the data or address line, sometimes the data and the address line is shared. Okay, so the control signal transmit both command and timing information among all the module. Okay, so you have 3 bus: address bus, data bus, and control bus. Okay, assume a three-stage pipelining. How many clock cycle you need? So you need 5 clock cycle, assuming each stage is 1 clock cycle. And there's no branching. So for the first instruction, you have fetch, execute, write. Second instruction, fetch, execute, write. Third instruction. So in order, all in, you need 5 instructions. Okay. So assume a processor employ a memory address register and a memory buffer register, a program counter and instruction register. This is a sequence of events. So if you have a memory address register, so you have a program counter, the program counter will go to the memory address register to fetch the address, all right? Where is the where's the address of the instruction. Okay, so you fetch the address, then go to the address. All right, then you fetch the memory. All right, contain the next address. Address is moved to the memory address register, placed on the bus. The control unit will require a memory read, and the result. So the control unit will do a memory read. Result will be on the memory buffer address. So then this memory buffer address will be loaded into the instruction, okay, to be executed. Okay, then the program counter will be incremented by 1. All right. All right. The program counter will be incremented by 1. This assume that this one is assumed that each instruction is 1 byte long, is 1 unit long. Okay? It can be 1 byte or 1 word, right, or double word. I don't know, right? It's architecture specific. List down the 6 stages, 6 flag. So you have a carry flag. So carry flag happen when you execute an instruction. There's a carry, okay? Right? There's a carry or borrow in the for the most significant bit. So let's say if you have moved AX to 0, then you decrement AX. So the carry flag will be set to 1. All right. The parity flag, if there's an even number of 1, all right, were produced when there's an even number of 1. So you can move AX, then you add AX to 1, so the parity will be set to 1. Okay. Even number of 1s, all right? Move AX to, let's say, 0x10, all right? Okay. So you add, the result is AX is equal to 0. So there is 2 1s. Parity back will be set. Auxiliary carry is that when there's a carry in the lower nimble to the higher nimble. Let's say if you have like this, and you add 1, or like this, you subtract 1. So you can see this lower nimble. You can see, okay. All right. So in this scenario, you will have the AX set to 1. 0 flag, when the 0 flag is clear. So you can give example when you move, when you add AX with AX. Okay. Then you have a sign bit, which result when there's a negative number. You also have overflow bit. Overflow bit indicate that the result is out of range. Example like this, you add 1, you'll be overflow. Okay. So you can write a program, and the result of execution will set one of the flags. All right. So this is some sample lab exercise. All right. Where you can try. Okay. So you can try program 1 will set the 0 flag. Program 2 will set the overflow flag, and so on. Right? So when you can set all flags, then you have mastered the first level of Kung Fu. Then the second level of Kung Fu, will be write a program that will set 2 flags together. How we're going to do it? This is a second level of Kung Fu. Second level of Kung Fu. Then the third level of Kung Fu. 3 flags, 4 flags together. They said. How do you do it? Right. The most write a program. Okay. Something for you to consider lah. If I give assignment or question, it will be like this lah. But unfortunately lah, I have no power. If you got power, I will give this kind of question. Okay. Any question so far? So far, any question? Okay, no, Okay. Assume okay, assume you have 4 stage. How many you have 4 stage pipeline, right? Assume there's no branching and 1 time unit per stage. So if you have 6 instruction, so you see here, you need 9 unit of time. So you can always, the formula is given here. So 4 plus 6 minus 1 equals to the 9 unit. So this tau is equals to 1. This tau is equals to 1, which is the 1 unit of time. So this is the symbol. Where's the symbol tau? Okay. This is this one. Okay. Then if you without pipelining, so you do it one by one, so you need 24. 4 times 6, you have 24 unit of time. So the speed up is 2.67. Okay. What would be the maximum speed up? Assume a 0 branching. So the speed up formula is nk plus nk divided by k plus n minus 1. So since n is large, for large n, let's say you have a large n, k plus n minus 1 is equal to n. So let's say n is 1 million, k is equal to 4. 4 plus 1 million minus 1 is more or less equals to 1 million, isn't it? So nk, this one will be equivalent to nkn, which is equivalent to k, which is the number of stages. So in this case, it is 4 lah. Okay. Okay. All right. Assume a processor employ a memory address register and memory buffer register, a program counter, and so on. Assuming it only support one address, it support one address only, then you can see here it's more or less same like 2 address, but except that you can see when you go to the memory buffer address register, you copy into instruction register, then this instruction register will copy back to the memory address register for the next cycle, because it's only one address instruction. Okay. All right. Anything you want to ask? Want to keep it short so that you can celebrate Chinese New Year? Okay, I'll stop the recording now. Okay.